Hello everybody. So today I've kind of got a little bit of a change of scenery here, namely the fact that I'm currently on my sofa, and I've got some paper instead of my whiteboard. I just figured I'd change some scenery just to, maybe jar some extra stuff in my brain or whatever. But nonetheless, I'm studying for my final exam right now in Stat Mech. It's on Friday. I'm recording this on Tuesday. I've done a little bit of studying beforehand, and I figured, hey, why not try and tackle some of these homework problems that we've got? And especially after I was given a review over the kinds of content that was expected to be on the exam, I usually just go over my homework and see what kind of stuff I have on there that pertains to the topic material at hand. So I guess I'm just here. I'm going to be narrating to you guys what some of this stuff is. In this particular video, I'm going to be going over a problem in Rife, and we will be intermittently interrupted by my cat. This particular question is 9.1 in Rife, if you are interested in trying to solve it for yourself. Basically, Rife says that we should consider having some sort of system of two particles, and each of these particles can be in any of three particular quantum states. Oh my goodness. So we have three quantum states, right? We have state 1, state 2, and then state 3, right? He gives us that the energies of each of these states, which I've designated as E1, E2, E3, they have respective energies of 0, epsilon, that is a 3, my bad, epsilon, and then 3 epsilon. Choosing the most confusing notation he possibly can, I can see. Anyway, so the system itself says that it is constantly in contact with some sort of heat reservoir at some temperature T. So if we have our ensemble here, right? Let's call this our ensemble. It would be in constant contact with some sort of reservoir, which I'm going to draw as a little kidney bean here that has some sort of temperature equal to 1 over K beta, right? Where beta is our Boltzmann temperature and K is our Boltzmann constant, K, right? Anyway, we want to find three things in particular here. In part A, oh my heavens, I might go back to using the whiteboard after this. It's just kind of me trying some stuff. Part A, he wants us to find what the partition function is for this particular system, assuming that they obey some sort of Maxwell-Boltzmann statistics. Maxwell-Boltzmann. Part B, he asks us for what the partition function would be if it obeyed some sort of Bose-Einstein statistics. And then lastly, he wants to know of what this partition function would look like if it obeyed Fermi-Dirac statistics. Now, before you jump into what the partition functions themselves actually are, I feel like it's handy to kind of refer to a table that Rife has in the textbook itself whenever we're determining some sort of system itself. Whenever we have something that is in Maxwell-Boltzmann statistics, we have to assume that each of the particles themselves are distinguishable first. So let me actually change the colors of my pen here. Do something first, so as I'm working through my solutions, we can kind of see where I'm going with this. So A. So for Maxwell-Boltzmann stats, we have to assume that our particles are distinguishable, right? What does that mean? Well, if they're distinguishable particles, it basically means that we can tell particle A from particle B apart from one another. We can tell which ones are these. So if we can tell which one is which, we can then construct every single potential configuration of these particles such that we don't have one that's redundant. So when we have this, what we can do is we can make a table of each of our energies. I'm going to call these, I'm just going to say energy is equal to epsilon. I wrote that down in my homework, but this is supposed to be an E. My bad. E1, E2 is equal to, I'll say 3 epsilon. No, epsilon. And then, oh my word, epsilon E3 is equal to 3 epsilon. Like I said, the notation is a bit confusing at times. So, let me get my camera lined up a little bit here. We'll have one state apiece here. Goodness, one state. And then we're going to have instances where we have two states, because we have two distinguishable particles. So we can have instances where our distinguishable particles are both occupying the same state, or they're occupying two different states, right? So if we, let's say we have holding this with my left hand ended up being a lot harder than I had anticipated, to be honest. But we're going to roll with the punches here. So in one state, we can have a possibility of having A and B, where A and B are distinct particles, in the equals 0 state. And then if they're both there, then neither of them are right there. Or we can have them in the E2 state. So we'll have A, B in the E2 state. And obviously, since they're both there, neither of them can be in the other positions. And then lastly, we can know that A and B can both occupy our 3 epsilon state. So for this, we know we already have three possible states, right? And lastly, what we have is whenever these guys can occupy two states, right? So we can say we have A and B in the 0 and 2, or we can have, and then obviously that one's not occupied, or we can have B and A. This one's not occupied. Or we can have A and B, and this one's not occupied. Or we can swap them around, say B and A over here. This guy is not occupied. And then we can say we have A, B, B, and A. And then neither of these guys are occupied. I know my table kind of sucks, but it gets the point across, I think. So all in all, we have 1, 2, 3, 4, 5, 6 more configurations, right? So consequently, with this, with these permutations of the configurations, what we end up getting is a relatively lengthy partition function, basically, right? So we can define our partition function in Maxwell-Boltzmann stats as being Z is equal to the sum of some number of particles R, right, of an exponential of our energy, negative beta times the number of particles in a certain state 1 times the energy of state 1 into E2 plus ... plus En, I guess NN for away, I guess. I don't know. This is just some amount. Or actually it'd be like R, because we're summing over R. I'm silly. But yeah, that's basically what we would get. It's kind of silly notation that Rife uses. Honestly, if we just wanted to, we could just write. This is a little bit more coherent. Do EXP, negative beta, ER, and R. So basically what this does is it helps us count the total number of energy states, and it also considers the degeneracy of each of these states as well. So if there are two particles in a certain state, that means that our degeneracy for that state would be equal to 2, if I'm understanding this right. More specifically, N itself is the number of states associated with the distinguishable configuration. So there we go. That's probably a better way of putting it. So for this case, what we would have is that we just basically go through each of our configurations and then consider the energy itself times the number of particles in that particular configuration. So we can go basically from top to bottom here. We would have E times negative beta times E1. So we have one distinguishable state here. So we'd have, actually this would just be 0 because epsilon's equal to 0. So it doesn't even matter if we count it. Technically there would be like a 2, I think, hanging out here. But because it's, well, not necessarily distinguishable. Well, no, they are distinguishable. What am I trying to say? I think that, yeah, no, there's 2 particles in the state. That's all. Oh my gosh, it's a weight of the number of particles in the state. I'm going crazy. That would be n. So energy times n. Plus E minus beta 2, because we have 2 in this next state for just epsilon. Then we plus E minus beta 2 times 3 epsilon, right? Oh my goodness. And then we have our degenerate cases. This is where I misspoke. So for our degenerate cases, those would be these guys down here, right? So basically we have 2 configurations per possible energy state. So this would have a degeneracy of 2. This would have a degeneracy of 2. This would have a degeneracy of 2, so on and so forth. So what we get is we get 2 times E minus beta times 0 times E epsilon beta, right? Because we have 2 here, 2 here. And we do plus 2 times epsilon negative beta times 0 plus E. And we have 3E here, so we have minus 3 epsilon beta. And we don't have like a multiplied by 2 here, and we don't have a multiplied by 2 here in this case, because there's only 1 particle apiece. So there's kind of a 1 hanging out here, 1 particle apiece in each of these states for the degenerate cases. And then last but not least, we do plus 2 times epsilon minus beta times epsilon plus, oh, I'm sorry, multiplied. I'm silly. These need to be multiplied together. Minus beta 3 epsilon, like so. And then we can just clean this up a little bit. Obviously, like this will go to 1. This guy will go to 1. Which other ones go to 1? This guy will go to 1. But, we can clean this up, and we can get a much nicer expression for this, frankly. And if we want to, we can actually, I'll flip this page over here. And we can write that our partition function ends up looking like z is equal to e to the power 0 plus, or we can just write this as 1. E minus 2 epsilon beta plus E minus 6 epsilon beta, because we can add. So, well, actually, this is a result of multiplication in the exponent. I'm sorry. 2 epsilon minus beta. Did I write beta twice? I did. Y'all, I'm very sorry today. I cannot speak. Save my dang life. Then we have 2 epsilon minus 3 epsilon beta. No, E negative 3 epsilon beta. I'm trying to say what each of these are. And plus 2 E minus 4 beta epsilon. And like I said, this is just kind of a result of just cleaning up the terms a little bit, adding some of these guys together. And we're really multiplying some of these guys together too, because that's what happens when we get multiplication between like 2 exponentials, right? So that's what this guy is a result of. Probably like on one of these guys on the other page. More specifically, like probably this guy here. Well, wait, not to be positive 3. Maybe the one that would result in that one. Yeah, it's in there. Yeah, it's in there. But yeah, that's what it looks like when you clean it up. But yeah, but that's the general principle for part A. We'll keep on going to do part B. Part B helps us to also draw another, to draw another table, but this time we're going to be dealing with Bose-Einstein statistics, right? So Bose-Einstein statistics, they're pretty similar to, oh my goodness, Maxwell-Boltzmann statistics, but in this case, the particles themselves are not distinguishable. So you'd be like operating with a bunch of bosons or something along those lines. So if we were to make our table again, epsilon 0, my goodness, epsilon 2 is equal to epsilon 3, epsilon. I'm just going to keep it this way because that's why I have it written in my homework, even though I have it, I'm going a little nuts here with the notation. So we have, draw some lines down here, like so, right? So what distinguishes these is that there's only going to be one state apiece, basically, where these particles can occupy some sort of unique instance. So like with the Maxwell-Boltzmann case, we had a few instances where we would have like A, B, epsilon 1, epsilon 2, epsilon 3, right? And this would be nothing there. Then we'd have, B, A, right there like that, nothing. So this would have a degeneracy of 2, right? But in the case of Bose-Einstein statistics, if we were to rewrite the same thing, these guys are not distinguishable from one another. So basically, these two instances of this configuration describe the exact same state. So that it only has a degeneracy of 1. So that's what that would basically result in. I think I'm describing this correctly. If I'm not, I'm going nuts. And someone can please just lay me out in the comment section. But besides the point, our table for our energies and our particle configurations for each of the states would end up looking like this. So we'd have A, nothing there, nothing there, nothing there, A, double A, nothing there, nothing there, nothing there. They're both in E3, right? Let me make this guy a little bit more because I'm going to need more of these guys. And then we can have one here, none there, none there, one here, and then one here, and then one here, right? So like I said, the degeneracy for each of these terms is 1, right? So we don't have to worry about some sort of scaling factor out front. But we do have to worry about, obviously, the number of particles that are occupying these individual states when we're constructing our partition function. So when we do that, we get for, oh my goodness, we get, if my camera would focus, it'd be so swell. Z would be equal to the sum. Once again, R, E, beta, N, R, epsilon, R. Right, and this is equal to the sum. Oh my goodness. I don't need to write the sum because I know what I'm summing over. So what we'd have is we'd have E minus 2, 0 beta for this guy all the way up here, plus E minus 2 epsilon beta plus E minus 3 epsilon beta. And then we need to configure these guys up here. And for those guys, we can just combine their sums in the numerator, basically. Oh, this needs to be multiplied by 2. Whoops. Because we have 2 particles. N is representative of the number of particles. You got a close up of my thumb. Anyway, for these guys, here, here, and here, we can express this as E minus beta. And we need to consider the particle and the state that it's in. So we'd have 0 plus epsilon, basically. We'd have 1 times 0 plus 1 times epsilon is basically what we get out of that, right? We have plus E negative beta, next guy, right? He would be epsilon, 3 epsilon. So we'd have epsilon plus 3 epsilon. And then last but not least, we'd have exponential minus beta. And we have 0 plus 3 epsilon. 0 plus 3 epsilon. Get a little close there. Once again, it's a little sloppy. I normally have this stuff written out and I can just kind of talk about it. I might do that in the next video where I just write out, do the problem, and then I try and explain it out a little bit better. So I'm not trying to do this in tandem. But we can clean this up, and what this ends up looking like when we do so is 1 plus e minus 2 epsilon beta plus e minus 6 epsilon beta. We get plus e minus epsilon beta plus e minus 4. Then e minus 3. Oh, word. Look at that glorious penmanship. I'm writing moon runes right now. Anyway, last but not least, we have Fermi-Dirac statistics, right? C wants us to know about Fermi-Dirac statistics. Now, with Fermi-Dirac statistics, something is really crucial here, in that it is, these obey the Pauli exclusion principle. Basically, if we have a bunch of accessible states here, right, and we have some fermion, or an ensemble of fermions that are trying to populate this set of, I'll do E naught down here, of available energy states. Epsilon. There we go. If we have a bunch of bosons, then we can say if we turn the temperature all the way down, then all the bosons are just going to kind of collect down here at the bottom. They're all going to be in the ground state. But in the case of fermions, you can't have them all coalesce in the same state. Once this lowest state is occupied by something, nothing else can occupy that particular state. So it's excluded from that energy level. So instead, you actually just get a stack of fermions. Fermion, fermions, fermions, right? Oh my goodness. Fermions. F is what I'm going to make on this exam if I don't get my act together. So, all in all, if we make our table for our Fermi-Dirac statistics, epsilon 1, epsilon 2, epsilon 3, we're going to have, also these particles are not distinguishable from one another as well, like we have in Bose-Einstein stats. So we make our table. It's going to be the smallest table of the day. Wish my papers wouldn't split, but we'd have A, nope, A, nope, A, in the energy, in the third energy state, and then we'd have nobody there, and then we just have them both hanging out over here. And then that's it. We can't have this happen where this guy's not over there, right? No, we can't do that, not at all. So what we do is we just make sure we don't stack them together in the same state, because like I said, we can't have them occupy the same energy state when we have fermions. But on the bright side, when we do Fermi-Dirac statistics, they end up having like the least lengthy partition functions out of all these guys. So let's cross this guy out here. What? That never happened. So we'll have, in this case, we'll have E 0 plus epsilon, because this is representative epsilon 0, 3 epsilon, right? Beta and minus plus E minus beta. Order doesn't matter because it's multiplication, right? And I'll distribute. Trying to fix my handwriting. There we go. Then we have 0 plus 3E, 3 epsilon. And then we have plus E, or epsilon plus 3 epsilon times negative beta. And then we can pick this up and make it nice. So we'll have like E minus 3 beta, and then plus E minus 3 epsilon. Oh my god, 3 epsilon beta. I think I'm dyslexic. E minus beta plus 0, so that's negative beta 3 epsilon, and then this is negative 4 epsilon beta, right? That's what that would end up looking like for that particular partition function. But yeah, sorry this was a little bit lengthy. I felt like it was a little bit longer than it needed to be just because I was writing this stuff out as I was going. But all in all, we have a pretty standard procedure. We look at the kind of statistics that we have for our ensemble, right? So we'll have either some sort of Maxwell-Boltzmann, Fermi-Dirac, or Bose-Einstein. And in the Maxwell-Boltzmann case... Hi, so I'm kind of a dummy, and I forgot to charge my phone, so my phone died literally mid-recording. But anyway, we have our Maxwell-Boltzmann case, where we have distinguishable particles, A and B, and we can configure them either in certain energy states together, because we can stack them, or we can put them individually in different energy states. Whenever we have some sort of distinguishable energy state, when we have a distinguishable configurations of these energy states, we call them degenerate, and we scale them by the number of possible ones that can be scaled. So let's say if we had like 4 allowed energy states, and we had like 3 particles, and we could have degeneracies up to like 3, that sort of deal. So we could have like A, B, C, A, B, any sort of permutation of that, right? So that's why we would scale this guy by 2, but then we'd have to multiply these guys together. Then we also have, obviously, just to review, we have our Bose-Einstein ones. In Bose-Einstein ones, our particles are not distinguishable from one another. So even if we had like an AB or a BA there, they wouldn't be distinguishable from one another. Or if we had an AB and a BA there, these wouldn't be distinguishable, so there's only one apiece. So we don't have to really worry about degeneracy, but we still have to consider the number of particles that are in those respective energy states, which is why we get those wacky little sums up in the exponent. And then last but not least, we have our Fermi-Dirac statistics, in which these particles obey the Pauli exclusion principle, and we have probably the simplest ones, where we can't stack them at all, and they can only occupy a limited number of accessible states whenever we're considering the possibilities. So yeah, make a table, add your terms up, obey the geometric series that you've got going on, or the exponential series it's got going on. And if you can do that, you're dandy.